Hello, today I explain about the fabrication process continually from before chapter. Part 17 is anti-reflection coating. First, in lithography, if we expose the light to mask, uh, then the reflection at silicon surface is occurred. This reflection can make some problems, so we should block this reflection by anti-reflection coating. So second is wave interference. First, we see this left picture. If two waves have same pace, then the two pace can have a summation by superposition theory. Then we can get this constructive interference situation. Um, These constructive interference have bigger intensity than before two waves, and right is destructive interference. If the two waves have a 180-degree phase difference, then by the superposition theory, the intensity is lower than before. Next is Bragg's law. Bragg's law is the relationship about the distance of two waves and wavelengths. So if you see this equation, if the two waves distance is proportional to the multiple integer multiple uh, to the wavelengths, then then these two waves must occur the constructive interference. So this constructive interference um, makes some problems at the lithography. If you see this picture, if this exposed light and these two reflection light have same phase waves, then these three waves can occur constructive interference at region A. So, so if the constructive interference is high, then the dose at region A is also high. The dose is about how much expose the amount of light to region A, and also how long take a time of exposing at region A. So if overdose situation, then region A can get a lot of photons than expected. So if you see this picture, in the positive photoresist, um, if the constructive interference is occurred, um, then the then the um, then the photons wave is bigger than we expected. So the curved pattern is occurred at this photoresist after lithography. So this means that the pattern is more small than we expected. Then this pattern is very weak, so this will make some problems like defect or other things. And also in negative photoresist, if the constructive interference is occurred, then the cross link is more occurred by this constructive interference. So the pattern is bigger than we expected. So solve these problems, we use anti-reflection coating. Um, in anti-reflection coating, there are two methods. So first method is top. This method is coated the anti-reflection material on the soft-baked photoresist. So this method use polynomial, polynomial like photoresist. So we should use the spin coating. And this method block the reflection by control the thickness and making a destructive interference. Um, this method have uh, cheap and easy to making advantages, but also have poor edge selective and also a solvent problem and ununiform coating problem. A solvent problem is that the uh, the anti-reflection material also have solvent. So this solvent melt the photoresist, and also this this material is so is so soft, so we can use this material by hard mask. And it is also have spin coating problems like ununiform coating. And next method is bottom anti-reflection coating. It is called as bulk. There, this bulk is coated on the silicon substrate before photoresist. So there are two types. First type is organic type. It is similar to the top method. So it is also use polynomial and spin coating, and it can also block the reflection at silicon substrate of silicon substrate by absorption at this bulk. It is also have similar disadvantages at top method. Next type is inorganic type. This inorganic type use silicon nitride by CVD, chemical vapor deposition by high temperature. Um, this type have a good edge selective and um, also have good anti-reflection and other things. And it is and this type have expensive and difficult to making and making time long making time disadvantages. Next one is PSM, page shift mask. Um, Solving the uh, constructive interference, we we change we change the mask characteristic for solving this constructive interference. So um, first type is attenuated PSM. If you see this left picture, original mask, at the original mask, if we expose the light, then at the pattern, mask pattern, the diffraction is occurred. So at the center, these two waves occur the constructive interference, then at the uh, at the wafer pattern, uh, at the wafer photoresist can get more photons than expected. So then the pattern result is like this. The center pattern is removed at positive photoresist. So we solve this problem. We use the material that change the phase by 180 degree. So we use this material at some part of mask pattern. So this diffraction wave, one diffraction wave phase uh, changed by 180 degree. So at center there is no constructive interference, so we can get a wanted pattern. Next method is alternating phase shift mask. This one is decrease the photoglass. So this decreasing can occur the phase shift by 180 degree. So it is also um, block the can it is also blocked the constructive interference. Next one is OPC, optical proximity correction. Uh, this one is also change the mask size or add the support mask for 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 get for getting a wanted pattern. So if you see pattern, this pattern is a wanted pattern. So this one is also mask pattern. After we litho, we can get this uh, real pattern. Um, in real, the at edge, the pattern is rounding. Because um, because if we expose the right is uh, the right have a diffraction. So the right exposed right at edge is um, sh- shortest than we expected. So the pattern is rounding. And at this point, mm, if we make this first line pattern and the second line pattern, the right is meted at some ports. So this make uh, constructive interference. So the pattern is bigger than we expected because of uh, many many amount of light at this region. So in real, so solve this problem, we make a mask uh, we make a customized mask. At the edge, we the mask size is bigger, and at this region, we make a small pattern mask like this. So this mask pattern can solve these problems. So if you see this picture, we can solve this pattern used by this support mask. So if we use the um, good positioning and size support mask, then we can get good pattern. So next one is OAI, off-axis illumination. Um, this one is before I explain about the diffraction waves. These waves can also have some problems. So this off-axis illumination is the solution of the diffraction diffraction problems by tilting the right to mask axis. So first is angle of next is angle of right axis. Before I explain about the Bragg's law, um, if we know about the right expose the right angle at two mask, and also we know about diffraction angle, we can get this Bragg's law equation. If these two waves, I, if the distance of two waves is proportional to the multiple integer multiple or wavelengths, then these two waves must occur constructive interference. So um, if the right axis is on axis, that is we expose the right vertically to mask. So the right exposed right angle is zero. So the so only this equation is existed. At this equation, the wavelength and the multiple wavelengths is fixed. So if the distance or distance between pattern and pattern is d value, right? Um, if d value is smaller, then the diffraction angle is bigger for fixed wavelength value. So um, uh, this uh, this situation can make a problem and not patterning. Because if you see these problems, if you see this picture, uh, if uh, the right, if the right pass through the mask, then the wave or diffraction wave have many information about this pattern. So these diffraction waves have many information about pattern. So if we want to the uh, good pattern, we should projection these uh, high order diffraction waves to the wafer. But at this picture, the high order diffraction waves can projection can't project to the wafer. So this one is this picture don't get a good nano pattern. So we solve this problem. We use the off-axis illumination. Um, if you see this picture, we tilting the axis like this. If we tilting this axis, then the diffraction wave we can um, we can project the diffraction waves to the wafer than before picture. So this means that we can uh, we can project the more waves or more information to the wafer. This means also get a good nano patterning. So um, also um, if we use the off-axis illumination, then we can get a small angle about the exposed light to the wafer. Because at before picture, the exposed light spread very broadly at length, so the exposed light to the wafer is very this exposed light have big angle, but this off-axis illumination, uh, the diffraction wave uh, in the small region, the diffraction waves is projected to the wafer than before picture. So um, the exposed angle is smaller than before picture. So this means is that the numerical aperture value is lower, and then the depth of focus is bigger. So it is means that we can get a nano pattern. Um, this is very um, important thing because the um, depth of focus have a trade of relationship at real numerical aperture at exposure machine. But if we use this off-axis, then we can solve this trade-off relationship or real, because we can't control we can get a good depth of focus without control the numerical aperture. So next is aperture type. There are four type. First is usually think about the aperture. Um, the first type is original type, original type, and this other type is selected by the type of mask. This dipole and quadrupole type is selected at line pat line pattern mask. So if you see this picture at this vertical mask, this dipole aperture have diffraction waves like this. Then this diffraction wave can have this region. So um, so this dipole aperture get can get a good non-patterning like this, and this light one is also have this exposed light region, and this quadrupole is selected at or line type of mask because this aperture have vertical and horizontal exposed line region. So you can use all type line pattern mask. And this annular aperture um, have have less resolution um, from other type. Um, this annular aperture can have less resolution than other type, but uh, this one can use at all type of mask because the exposed light have all direction uh, light have all direction, so we can use all type of uh, mask. Next, part 21 is double patterning process. Um, mm, if we make a nano patterning, this double patterning process is most used at present. So first, double processing, double patterning process method is litho-edge process. This LE method have two approaches. The first one is double trench approaches. Um, if you see this picture, uh, first we photoresist lithography, and first photoresist lithography, and next etching the hard mask, then we can the trench. This trench have very small critical dimension. So for nano patterning. So next, we also second photoresist lithography, and next uh, etching the hard mask and strip photoresist, then we can get this wafer. And next, also we have etched this hard mask and the silicon dioxide, then we can get non-pattern. Um, this litho etch method is have process. Um, First we litho and second etch, and this process is repeated, so we call this LELE process. And next one is double line approach. Um, it is also have a photoresist, and next etch process is repeated. Um, this first double trench approach have some advantages of a critical dimension. So this one is used for metal lining between transistors. So like this. And next, this double line approach is used at polylayer or used for channel. So channel like channel and poly layer. So this LELE method is used for making memory. But this method have overall problem. If we in the photolithography process, if we have a mask misalignment, then the pattern is also have a misalignment. So this means that the distance between pattern and pattern is unequal. So so this means if we um, before chapter we explain about the parasite capacitance. So the capacitance is existed at like this. So the capacitance is uh, like this. Um, if the distance of this pattern is bigger or smaller, then the total capacitance is also bigger. Then this occur the time constant um, or bigger. Time constant is also bigger. Then this means that performance is down. So next double patterning method is self-aligned double patterning. Uh, the difference um, the difference from LE method, this self-aligned double patterning have just one photolithography and also use the self-aligned mask um, without put mask. So If you see this picture, after the photolithography, we um, we etching the bulk and hard mask forget a hard mask renderer. And next, we dispose the spacer at renderer, and we etch back the spacer by top-down etching and also hard mask remove. And also using the self-aligned mask spacer, we make a aligned pattern, and next we can get a nano pattern. So this vendor is mean that the important pillar or axis at this double patterning method. So if we deposited the thin spacer, we can get very thin spacer at this process, very thin. And if we same process such as spacer deposition and hatchback at this thin spacer, then um, more we can get more we can get a good nano patterning than before. This means that this the self-aligned double patterning or self-aligned quadra patterning is good process for small critical dimension. So so if we repeat this spacer deposition and hatchback process hatchback at the spacer renderer, uh, this this process is called as self-aligned quadra um, patterning. Um, this self-aligned method also have problem if um, we etching the hard mask renderer at first, if we not if we are uh, not good etch at hard mask, then some we can get a smaller or bigger critical dimension than we expected. And also at the hard mask renderer remove process, um, if we etching this renderer, this etching damages the spacer inside and outside. So if you see this drawing, uh, the outside of spacer is the inside of spacer is damaged, very big damage, and outside is small damage. So the pitch distance is long and small, and long and small is repeated. So this is room like um, a human working. So this problem is pitch working, and this problem also is similar to overlay. This one is also affected to the parasite capacitance and um, other nano-patterning problems. So uh, that's all. Thank you for listening.